So for the next speaker of the session, we have Lana Bozanic, and she's going to talk about correlation harvesting between particles in uniform motion.
Okay, sure. All right, hello everyone. Like it was said, I'm Lana Bozanic, and today I'll be talking to you guys about a recent work that I did with Minar Naim, Kensuke Gallic Yoshimura, and Robert Mann about correlation harvesting between particles in uniform motion. So first we'll begin with some background. So there were two main motivations for this project, the first being the Unruh effect, which I'm sure many of you are familiar with, which is a remarkable prediction of quantum field theory that tells us if we have a linearly accelerated detector, it will experience a thermal bath with temperature TU that is proportional to its acceleration. Now, because of its significance, there has been a lot of interest in trying to experimentally prove this effect. But there are a lot of hurdles in trying to do so, one of which is that you would need an acceleration of about 10 to the 20 meters per second squared to even see 1 Kelvin of temperature. Now, because of the experimental implementation interest, there has been a lot of different studies done in the different trajectories that we can sort of see the Unruh effect or Unruh-like effects in the lab. So, for example, the circular trajectory is of interest because we can manifest it in the finite lab setting. So many studies have been done about the Unruh effect and similar effects for different types of trajectories. And then we also have the correlation harvesting protocol, which is less understood compared to the Unruh effect. And this essentially states that two detectors will become entangled through local interactions with a quantum field. Now, what we wanted to do in our paper was to investigate this correlation harvesting protocol for the most general type of uniformly accelerated detector. And what we found out is that there are 5 different classes of motion, or 5 different classes of uniform motion that were characterized by Lita. So we want to understand correlation harvesting just in this more general way, because there have been studies done for linear trajectories and circular trajectories, but we want to understand it from the most general perspective. So I know the next few talks are also about the correlation harvesting protocol, so I'll briefly review it here. So like I said, this essentially states that if we have 2 UDWs in a quantum field and each have energy gap omega between their ground and excited states, and they are traveling along certain trajectories in the field, after a certain time they can become entangled with one another. And so the Hamiltonian that describes each individual detector is governed by this equation, where lambda is the coupling strength, chi is the switching function, which controls the duration of the interaction between the field and the detector. Mu is the monopole moment. And then finally, this last term is just the value of the quantum field along the trajectories that we send our detectors on. And then with this, we can define the total interaction Hamiltonian for the entire system. And then if we start with some initial state, we chose everything in its ground state. So detectors A and B in their ground states, and the field in its ground state. We can use perturbative analysis with the Hamiltonians described in the previous slide to evolve our state. And then finally, when we trace out the field, we're left with this density matrix that describes the joint state of detectors A and B. And this density matrix gives us all the information we need to understand the correlations harvested from the field. So these LAA and LBB terms are our transition probabilities, so the probabilities that our detectors will transition from the ground to excited state. And then this LAB term is used in quantifying the total amount of quantum mutual information. And then this last off-diagonal M term is used in quantifying the total non-local correlations that are extracted from the field. So in all these terms, this Wightman function, or the 2-point correlation function, comes up, and in 3+1 Minkowski spacetime, which we consider, it assumes this form. And throughout our entire study, we use Gaussian switching to control the duration of the interaction between the field and the detectors. So using all the information from this density matrix that results from the protocol, we then have a measure of the extracted correlations. So for now, we'll just talk about the entanglement. And for our study, we used concurrence as the measure of entanglement, which is defined using the M term from the density matrix, which once again quantifies the non-local correlations and the transition probabilities. So now that we've reviewed the correlation harvesting protocol, we can talk about the different types of uniformly accelerated trajectories. So Lee-Ta found that there are actually 5 different classes of uniform motion that can be characterized just using 3 different parameters. So the first parameter, is the curvature, which describes the direction of the acceleration, and then we have 2 torsions, B and nu, and these can intuitively be understood as a sort of rotation in axes perpendicular to the direction of the acceleration. So these 5 classes of motion are linear motion, which is characterized by non-zero acceleration, but the 2 torsions being equal to 0 with this trajectory. Then we have catenary motion, where A is greater than B and the second torsion is equal to 0. Then we have cusped motion, where A and B are equal and the second torsion is equal to 0. And then the last case where the second torsion is equal to 0 is the circular case, where A is less than B. And then finally, the most general type of uniform motion is where we also consider the second torsion being non-zero. But we don't consider this case in our paper, so I'll skip over this section here. So like I mentioned, this in 3+1 Minkowski spacetime, the Wightman function assumes this form, and obviously it's very heavily dependent on the trajectory we take. And what we found is for all the different classes of motion where the second torsion is equal to 0, we can find a stationary and a non-stationary version of this Wightman function. And so what we mean by stationary is when the Wightman function is time-translationally invariant, so it only depends on delta tau. And non-stationary is when we also have this delta plus tau dependence. And so for all of the 4 uniform motions that we consider, we can find this stationary and non-stationary scenario. So for example, in the linear case, the stationary motion is when the 2 detectors are traveling parallel to each other, but a non-stationary configuration is when they are following each other. And then, like I said, for every single type of motion, we can find this stationary and non-stationary scenario. So that was catenary, then we also have cusped, and finally circular. So just, So the interesting part about all of this is that although all these trajectories seem very different at first, we can actually categorize them with a master Wightman function. So for the stationary scenario, we have this one Wightman function that can use to be described all those different motions: linear, cusped, catenary, and circular. Similarly, for the non-stationary scenarios, we have this one master Wightman function that only differs by this term here, which has this delta plus tau dependence that makes it non-stationary. And what you'll notice in these 2 generalized or master Wightman functions is that they have this new parameter b bar right there that is just defined as b over a. So for linear, it's 0. For catenary, it's between 0 and 1. For cusped, it's 1. And for circular, it's greater than 1. So these Wightman functions, if we just tune the value of b bar, we get the different types of motion, which is really interesting. We have just these 2 Wightman functions describing the stationary and non-stationary scenarios for all these different types of motion. So now we can understand the correlation harvesting protocol as a function of the different types of motion. So just to summarize all this background, so we start off with the correlation harvesting protocol, and this yields these 2 terms to calculate. Then we have these master Wightman functions that describe the Wightman functions for all these different types of trajectories just by tuning the parameter b bar, which is b over a. And then finally, to measure the amount of entanglement extracted from the field, we use this correlation measure of concurrence. So now we can move on to the main results of our paper. So the first thing we did is we tried to understand how acceleration affected concurrence. And what we'll see in both the stationary and the non-stationary scenarios, the concurrence will die with finite A. Another thing that we noticed is that for B bar less than or equal to 1, so for the linear, catenary, and cusped motions, the stationary case will always harvest more entanglement than the non-stationary case, but this pattern doesn't hold anymore for the circular regime, and although it's a bit hard to see in on these figures, and it'll be more clear in the next, the non-stationary scenario actually oscillates around the stationary scenario. And then when we plot the concurrence as a function of B bar, this is a bit more apparent. And so when we analyze how the harvested entanglement as a function of the trajectory, or B bar, we see that as B bar grows larger, we can harvest more and more entanglement. And once again, we see this pattern that the non-stationary case will always harvest less than the stationary case if we're in the linear, catenary, or cusped regimes. And we see this oscillation behavior in the circular regime when B bar is greater than 1. And this oscillation is a lot more pronounced for larger accelerations as well. Now, another thing that we were interested in understanding was when can we actually harvest entanglement? So in the case of inertial detectors, it's known that no matter how far you separate your detectors, you can always find an energy gap omega so that you can still harvest entanglement. So we wanted to see if this was still the case, if our detectors were uniformly accelerated, and unfortunately, this is not the case. So this figure shows the regions to the left of all the curves in this figure shows the regions where we can still harvest entanglement as a function of the separation distance and omega. So we see that we can't always harvest entanglement. We can't always find parameters that allow us to harvest entanglement. In particular, one implication of this is that we can't always, or we can't at all, causally separate our detectors and still harvest entanglement. And so that leads us to our next question of if we're ever genuinely harvesting entanglement. So in the entanglement harvesting protocol, we can break up our Wightman function into two parts, an anti-commutator part and a commutator part. And these separate parts essentially tell us about how much entanglement is actually extracted from the field and how much entanglement comes from communication between the detectors. And so we know that if we causally separate our detectors, all the entanglement will always come from just the field. But if they are in causal contact, they can potentially still communicate, and entanglement can arise from this communication and not just the field. So yeah, this Wightman function can get split up into its real and imaginary parts, or the Hadamard part, which we call the genuine harvesting, and the Pauli-Jordan part, which is entanglement from the communication. And then we can split up that M term, which quantifies our non-local correlations, and introduce concurrence quantifying both the genuine harvesting and the entanglement from communication. And what we ended up finding is that even though we can't causally separate our detectors, even though we can't causally separate our detectors, we can still tune our parameters so that the harvesting is genuine harvesting. So this figure shows the solid lines. The red is linear, the blue is circular, and the solid lines represent the genuine harvesting, and the dashed lines are the entanglement from communication. And so on this figure on the left, we can see that this region where the dashed lines are 0 and the solid lines are non-zero, that is genuine harvesting, even though our detectors are still in causal contact. So yeah, that is, oops, forgot to put that up there. But that is all I have for you guys today. I just wanted to end with a brief land acknowledgement. Much of the research conducted for this project took place on the traditional territory of the neutral Anishinaabe and the Haudenosaunee peoples, and I just want to say how thankful I am to get to work and do what I love on this land. Thank you.